Alright, so today I'm going to be explaining another beautiful paper. This paper with the title pathGCN, Learning General Graph Spatial Operators from Paths. This interesting ICML paper in 2022, very important paper. Graph convolution networks, similarly to convolutional neural networks, are typically based on two main operations, spatial and pointwise convolutions. In the context of graph convolutional neural networks, differently from CNNs, a predetermined spatial operator based on the graph Laplacian is often chosen, allowing only the pointwise operations to be learned. However, learning a meaningful spatial operator is critical for developing more expressive GCNs for improved performance. In this paper, we propose pathGCN, a novel approach to learn the spatial operator from random paths on the graph. We analyze the convergence of our method and its difference from existing GCNs. Furthermore, we discuss several options of combining our learned spatial operator with pointwise convolutions. Our extensive experiments suggest that by properly learning both spatial and pointwise convolutions, phenomena like oversmoothing can be inherently avoided. So this is a spatial operator induced by a smoothing kernel on different graphs. This is an operator. So this is we call it spatial operator. And these are the contributions of this paper. Because pathGCN supports several formulations similar to CNNs, ranging from global to per layer and per channel learned spatial operators. So what is the spatial operator, for example, in graph convolutional networks? Typically, GCNs involve two main ingredients, spatial and pointwise. The majority of GCNs employ a spatial operator based on the graph Laplacian. For instance, the spatial operation in this paper can be obtained like this. This is a combination of 1-by-1 convolution and operator P tilde. And random walk on graphs. So what is the method? Learning this spatial operator. So given a tensor F, the convolutions in CNNs denoted by KF is a linear operation. So we present a methodology that allows the construction of graph convolution that is similar to standard convolution on a regular mesh grid. So assume first that we have a single channel feature tensor F and a path of length K. Let us denote the learned spatial parameters by S, and let Y be a tuple of node indices of a single random path of nodes of length K starting from node J0. So this is the convolution over a single path for a Jth node. So you see it's a linear operator similar to the CNN. So it's a convolution over a single path. Now that you understood just a single channel for a single path, so that is the features of nodes on the path Y sub j are weighted by the corresponding learned parameter in S and summed to get the feature of the Jth node. So instead of considering just a single path, now we have p paths because summation was over yj, but we have this summation over, we have p different paths. And here we want to construct a pathGCN. So we need to add channel mixing convolution and nonlinear activation. So that was interesting. Everything is about this single channel where you move to p paths, different paths, and that's it. Because this kf is now here, and then you update it in the next layer. So we have constructed a pathGCN. Very interesting. So this is the effective spatial operator from a walk of length 3 starting at the dash nodes. This is how we construct. We need the path in order to construct. So we need the random walks in order to construct that. And now let us consider a simple case of a convolution on the general path of length 2. So the expectation of this one can be written like this. And now consider of a path of arbitrary length. Instead of 2, now we have length k. From 0 to k minus 1, it means we have k. And then you can see the computational cost of that. But they experimented on Cora data that cites here these data sets that are more that have more homophily rather than heterophily, so it's simpler. Oh, but by the way, this Chamel-Sun is really hard in comparison to others, of course. Chamel-Sun is very hard because it has more heterophily. And so this is a visualization of learned spatial because we are learning it from an 8-layer pathGCN trained on Cora and applied on the dash node in the graph top and its corresponding learned weights on the bottom. So this is a fully supervised node classification accuracy. As I said, this Chamel-Sun is very hard, and as we expected, it has lower node classification accuracy. And then protein-protein interaction dataset is also very interesting. If you want to do inductive learning on that, you can compare the F1 score of GraphSage, these baselines that we know, with the pathGCN. So from GraphSage to pathGCN, we have huge improvement in our F1 score. Of course, even graph attention is also similar to this. So it's a slight improvement to your graph attention. Of course, I wrote a paper that with the name graph structure attention, which I generalize graph attention, because then I attend to this local structures around each node to have a better expressive power and better attention. Oh, this data set, we use these important data sets for graph classification. And they compare it, for example, if you compare with graph isomorphism network, you see some improvement.